Hey there, in this video we are going to talk about polynomial functions. Specifically, we want to learn how to find all the important features of the graphs of polynomials and come up with a vague or general sketch of what that polynomial looks like without needing any technology to help us out. So first we want to talk about what polynomial functions are, because not everything is a polynomial function. And we start with a power function. It's like a simple version of a polynomial that has less rules attached to its definition. So a power function is just one term. It's got x to some power. It's got a coefficient multiplying out front. So it looks something like this, kx to the p. There's not a lot of restrictions on k and p. They just have to be real numbers. With polynomials, we put a lot more restrictions on what the coefficient and the power can be, just because when we make these restrictions, it kind of guarantees us some specific features about the graphs that we'll be looking at today. So with a polynomial function, it's very much like a polynomial that we've been dealing with in the past. We're just now turning it into a function. The coefficients are real numbers, and the exponents have to be non-negative integers. So that's 0, 1, 2, 3, 4. Those are my non-negative integers. If you see a negative exponent anywhere, then we're not dealing with the polynomial, and the rules that we're going to talk about in this video don't quite apply in those cases. Okay? So it's usually just a series of terms, similar to the power series. There's just a bunch of them. Okay, so some characteristics that we want to be aware of, or we want to be able to identify about a polynomial. First one is the end behavior. This is what's happening at the end. With polynomials, usually there's some interesting stuff happening in the middle where things are curving up and down. And then at some point, things eventually will go to infinity or negative infinity. Now, the degree of the polynomial tells me what the end behavior is without even having to plug that in or graph it. So we're going to look at what happens as x approaches positive infinity, so going off to the right from the origin, and as x approaches negative infinity, going off to the left. You'll notice here that I'm using these arrows. That arrow is read as approaches. An arrow we're going to start to see more and more as you get closer and closer to calculus. So that reads as x approaches negative infinity and x approaches infinity. So if the degree of the polynomial, which just a refresher, the degree is the highest power of any of the terms in the polynomial, if it's an even number, then the polynomial is going to go off to infinity as x approaches plus or minus infinity. So like this parabola we see here, it's going up to infinity on the left and the right. If the degree is negative, it's going to go up to the right and it's going to go down to the left. So as x approaches negative infinity, f of x will approach negative infinity. As x approaches positive infinity, f of x will approach positive infinity. That's what all that notation is saying there. Some other characteristics we want to know is, I told you, these polynomials tend to curve up and down, get some waves going there. Whenever it changes direction, we call that a turning point. So if it goes from increasing to decreasing or decreasing to increasing, then that's a turning point. It's usually a local or max absolute extrema as well. But we also can refer to that as a turning point. The x-intercepts, we're going to start referring to those as the zeros or the roots of the function. Okay, that value where it hits the x-intercept, these are really important to coming up with a sketch of the graph. So we're looking for the x-intercepts, and that, remember, is when f of x or y is equal to 0. So I can find the zeros and the roots by setting the equation equal to 0. Now, some rules about the amount of turning points and zeros you'll have in a function goes back to the degree of the polynomial. If the degree is n, then you will have at most n zeros, possibly fewer, and at most n minus 1 turning points. So if I have a polynomial that is the 5th degree, so its highest power on an x is 5, then there's no way there's more than 5 zeros or x-intercepts. Okay, there could be less, but no more than 5. And there's no more than 4 turning points. So it can only change directions 4 times at the most for a 5th degree polynomial. One of the ways that we will find the zeros of a polynomial is to factor it. See, usually the easiest way, if it's factorable, we can factor it, and then each one of those factors is going to indicate what number that factor will zero out at, and we can find our roots from that. So if I can write the factors as x minus x1, x minus x2, and so on, then that x1, x2, and so on, those would be the roots of the polynomial. The number of times a root appears is called its multiplicity. So I said at most you can have n roots. One way that we end up with fewer roots is if one of them is a multiple root or has multiplicity to it. An example of what this looks like is, let's say I have the polynomial x minus 1 squared. Well, 1 is a root here because if I plug in 1 for x, I will get 0 for the polynomial. And the factor is squared. I have x minus 1, that factor, squared. And so that is a multiple root. It has a multiplicity of 2. Okay? If it was a third power, its multiplicity would be 3, and so on. And what the multiplicity tells me about the graph is what the behavior is at that x-intercept. So if the multiplicity of a root is even, like this example here, then that means that the curve is going to approach the x-axis, hit it at the root, and then go back in the other direction. It's a turning point at that spot. If the multiplicity of the root is odd, then that means it's going to go through the x-axis and carry forward. So if it's going up to the right as it approaches the x-axis, it's going to continue going up to the right after it crosses the x-axis. So it kind of bounces back. If the multiplicity is even, it carries through the x-axis if it's odd. So just factoring and identifying the roots and their multiplicity gives us a wealth of information about the graph of a polynomial. Okay, so we're going to take all this information and put it together to come up with the sketch of a polynomial. A comprehensive graph of a polynomial function should have the following things. All the zeros, those x-intercepts, need to be identified. The behavior at those intercepts, so is it passing through? Is it a turning point at that x-intercept? The y-intercept, usually just one of those. The sign of the function between the intercepts. So am I above the x-axis? Am I below the x-axis? So we're just kind of where the curve is located will tell me that. And then the end behavior. Is it going up to infinity? Is it going down to infinity at the ends? Okay, so let's look at an example. Here we have f of x equals 3x to the 4th plus 6x cubed plus 3x squared. And we want to be able to sketch this thing. So all that stuff we just mentioned, we're going to try and include here. So let's start with the degree, because that tells me a lot about what is going on with this graph. The highest power of this polynomial is that x to the 4th. So the degree of the polynomial is 4. So I'm going to aim to find 4 roots at most. That might include their multiplicities. But that's what I'm looking for, is 4 roots or zeros that are hitting the x-axis. It also tells me the end behavior. Because the degree is even, I know that as x approaches infinity, and as x approaches negative infinity, the graph is going to be going up to infinity. Okay, so I already have this idea that it's going up to the left and to the right. I just now need to figure out what's happening in the middle. So I'm going to start factoring this thing. Okay, I can factor a 3 out of all of those coefficients, 3, 6, and 3. And all of the terms have at least an x squared, so I'm able to factor out 3x squared from the polynomial. And that leaves me with x squared plus 2x plus 1 in parentheses, multiplying by that 3x squared. So now I have a trinomial here that I can factor. X squared plus 2x plus 1 factors into x plus 1 times x plus 1, which I can write a little more compactly as x plus 1 squared. Okay, so I can see here that I've got some multiple roots going on. So let's identify the zeros. So when is this function going to be equal to 0? Okay, so I'm plugging in 0 for y here. Now, that 3x squared tells me that if I plug in 0 to this function, then that zeroes out the whole right side. I get 0. So x equals 0 is a root, and it's squared, so the multiplicity of that root is 2. If I move to the next factor, x plus 1, well, I get another root from that, negative 1. And x plus 1 is squared as well, so it also has a multiplicity of 2. So looking at my roots and their multiplicity, I'm at 4. I've got 2 zeros and 2 negative 1s. I know I found all the roots. I don't need to worry about looking for anything else. So those are my roots. They're even, which tells me that those are going to be turning points on the graph. It's not going to be passing through the x-axis. Next thing I want to find is the y-intercept. I need all the intercepts to graph this thing. So I'm going to plug in 0 for x, and it turns out when I plug all that in, I just get 0 for the whole thing. So the y-intercept is 0, 0. Okay, so I've got a lot of information here that I can start to put together into my graph. You might start with a really general sketch with some arrows going on like this. Here I've got my roots identified. My y-intercept happens to be one of my roots, and I know it's going up at the ends. So the only way for all of this to happen is for it to be coming, so it's decreasing towards negative 1 because it's an even multiplicity. I know it's going to bounce back up rather than pass through the x-axis. And so that means at some point it has to come back down again to get to the 0 root. And then from that one is also an even multiplicity. So again, it's going to bounce back and start heading up to hit my end behavior. So my sketch looks like this when I'm all done. I don't really know how high that point in the middle is. We weren't asked to find any extrema here, just these basic major pieces. So that one would be one that would be a little bit harder to find. That's when we get into some calculus methods to find exact values for things like that. So you won't be really asked to find any of those absolute minimums or maxes unless they happen to be really nice numbers. Okay, so that is how you sketch a polynomial function. There's an example below this video for you to practice some more.